Okay, let's take a further look at differentiating functions with natural log x and then using these properties. Now, what are the properties? So this should be review, but now we're specifically going to use it while we're doing derivatives. If we have a product of anything in that we're taking the natural log of this product, right, x times y, we can split that up to natural log x plus natural log y. Well, the second one kind of makes sense directly from that, right? The opposite of multiplying is division, so the opposite of addition is subtraction. Okay, the third one we have already used as well. Some of these have kind of popped up already, but we're going to use them in a big way in the first two examples. So if we have an exponent b, we could bring that exponent down. The last property is e and natural log are inverses of each other. I want to include this one because it is kind of weird to have e to the ln x. Like, why does it cancel to just x? So it is a property. We won't, again, look at y in this video, but it also works if we had natural log of e to the x. Okay, e and ln next to each other, think of them as just canceling out. All right. So using this first property in this first example, I have natural log of this multiplied by this multiplied by this. Even though I just did x times y for the property and change it to an addition, it works for, no matter how many things in here, if it is all multiplied, which it is, right, parenthesis, I can rewrite this then as y equals ln x plus 5 plus ln 2x minus 1 plus ln 4 minus x. Now when I do derivative, I have three natural log functions. And remember, derivative of natural log is really easy. You do the derivative of that. So derivative of x plus 5 is 1 over x plus 5. The derivative of 2x minus 1 is 2 over itself, right? du over u. du over u is the derivative of natural log. And last, we have the derivative of ln 4 minus x. So the derivative of 4 minus x is a negative 1, or we could change that plus to a negative, right? It doesn't matter. Over itself. And that's it. I mean, we could get LCD and all that, but this is perfectly fine. The point is we want to see how to do derivatives of this. I'm going to take it a step further even and say with a little practice and kind of looking ahead, you can actually do quite horrible problems in your head. So what do I mean by that? Well, I'll prove it. I'm going to write the answer to this next one down here, but then we'll actually go through the steps. So I'm doing derivative of both sides, right? So that derivative, I know that this gets split up to plus. And then I could see this property number 3 in which the exponents can come down. And then I know the derivative of this is just the derivative divided by itself. So let me prove it, and then we'll go back through and go through all the steps, right? Okay. So we have this derivative is going to be that 2 that we brought down multiplied by the derivative of the inside is 1 over 1 plus x plus 3 multiplied by the derivative of the inside is again 1 over 2 plus x, and then plus 4 multiplied by derivative of the inside is 1, 3 plus x. Maybe I should have picked a better example where all the derivatives weren't 1, but that's okay. And really, there's nothing else to do. The derivative is 2 over 1 plus x. I could rewrite it to clean it up a little. 3 over 2 plus x and 4 over 3 plus x. Okay, now let's actually go through steps and let's verify that I could in fact do it all in my head. So first off, the natural log says I can split these products to multiply, right? So y equals ln 1 plus x squared plus ln 2 plus x3 plus ln 3 plus x to the fourth. Next property is number 3. It says I can take the exponent and bring it down. So this function is 2 ln 1 plus x plus 3 ln 2 plus x plus 4 ln 3 plus x. Now when I do derivative of both sides, I'm doing derivative. Sorry, I didn't mean to choose Christmas colors here, but that's all right. Okay, so when I do derivative, I'm doing derivative of each piece, right? So the constant stays, there's the 2. And the derivative ln 1 plus x is this, right? 1 over 1 plus x. Here's the 3, the constant. Here's the derivative of the natural log. The 4, the constant. The derivative of ln 3 plus x. So you can see, right, these properties make derivatives of natural logs significantly easier. Otherwise, we would have had some crazy chain rule in here to do all that. All right, now it's like you get the hang of this, and yay, we found an easy derivative. You know, I'm not saying it looks clean, but easy. And then we get to this next example. Here's the difference. We have ln and ln. We have a natural log of some function multiplied by natural log of some other function. I can't use these properties, right? The property says natural log of x times y, not natural log times a natural log. Unfortunately, this one, we don't get much love here. We're going to have to just go our old way. F is this first thing, ln 3x plus 1. F prime is 1 over 3x plus 1. Or, I'm sorry, 3 over 3x plus 1, right? Derivative of 3x plus 1 is 3. G is ln 5x plus 1. G prime is 5 over 5x plus 1. So the derivative is f prime g, 3 over 3x plus 1 multiplied by ln 5x plus 1 plus fg prime ln, so I'm going to go ahead and just write the 5 first, ln 3x plus 1 over, right, it was 5 over 5x plus 1. Because we're multiplying, right, I just put the ln's in the numerator because they were over 1. Now, can we clean this up at all? Not really. I don't know if this looks any better, but we can go and use property 3, right, where the number out front, we could go backwards, like we could bring the exponent down, or we could bring the number back up to the exponent, but I don't know that that necessarily looks any better. ln 5x plus 1 to the third power over 3x plus 1 plus ln 3x plus 1 to the fifth power over 5x plus 1. Okay, take your pick. I think either of those solutions. I wouldn't say one is more simplified than the other. Okay. Moving on. This last example, I'd said we would talk about this later. Well, here's later. We kind of needed this idea of logarithmic differentiation to, in fact, show what the derivative of this is. So in a previous video, we talked about this, and the derivative of 2 to the x is simply 2 to the x, but then we multiplied by natural log of that number, right? So natural log of 2 times 2 to the x. Remember, derivative of e to the x is ln e times e to the x, right? ln e times e to the x, but ln e is 1, so we didn't need it. So what we are doing here is actually showing, like, all right, why is that true? So logarithmic differentiation, what is the purpose behind it? First off, if we look at the first example, if I wanted the derivative of all of this stuff here, I would need a triple product rule without this natural log, right? So the idea is like, if you have some crazy complex function, maybe do ln on both sides and then do derivative. And the reason you would do that is because ln makes it simpler to work with because of the properties it has. Okay. I'm choosing to do an easy one to verify that the derivative is this. And, we're not going to use this method too often, so did want to demonstrate it, but not go into great lengths. First off, let's change f of x to y. Here we have y equals 2 to x. So logarithmic differentiation says, let's do natural log on both sides. And why would we do that? Well, suppose we didn't know derivative of 2 to x, right? This is actually deriving the rule. I don't know what derivative of 2 to x is, so if I do natural log, I can figure it out. Now, why can we figure it out? Because the property says now I could bring that x down. And ln2 is just a constant, right? If I plug that in a calculator, it'd give me some number. Some number less than 1. I don't know exactly what it is, 0.07 or 0.7 or something like that. Doesn't matter. Okay. Now it says use the logarithmic differentiation to differentiate. So we're going to do derivative d over dx. Okay. So the derivative of the right side is actually really easy because the derivative of x is 1. And then I have ln2, which is constant. So, think of this as like 3x. The derivative of 3x is 3. So the derivative of ln2x is just ln2. Now the derivative of natural log of y. First off, I'm doing it with respect to x. So anytime you have respect to x and you don't have that x, right, you have to include dy dx. So I have that there. Now we can look at, well, what is the derivative of natural log of y? Well, the derivative of y is 1, and then, right, natural log y. So you do derivative of y is 1 over itself, 1 over y dy dx. And what's our goal? Our goal was to find the derivative, find dy dx. So therefore I want to isolate this, right? Well, I have 1 over y. Multiply by y on both sides to get rid of it. Okay. Now we only have dy dx equals ln2 times y. Well, I want x, I don't want y, but if we look at the original problem, right, we said y is 2x, right? F of x is 2x, so y is 2x. So I'm going to plug this 2x back in for y. So therefore we have ln2 times 2 to the x. That's exactly what I had claimed it would be, right, with the formula. But now we actually showed why it's true. We use this log as a trick to get x down in order to come up with the formula that I told you to use.